In this video, we're going to be covering probably the most common form of proof. And the idea is it's a direct proof. And this is for an if and only if statement, or if you like, a conditional statement. And as just a slight reminder, remember that if we have a conditional statement, if P, then Q, remember it's false exactly when the if part is true and the then part is false. So I like to call this situation where the if part is true and the then part is false the dreaded row. And that's what we want to show. We want to show that this just will never happen. So a direct proof, again, is, well, we're going to assume that the if part is true. We're going to assume P is true. And we're going to show that Q, the then part, must be true, that we're never in this dreaded row. Remember, that's what you're trying to avoid. So that if P is true, there's never a situation where Q is false. And that way, this dreaded row will never come up. And the steps for these direct proofs are basically the same. Let me write them down and then we can talk about the example. And I don't want to say steps as in if you follow these, you will easily do a proof. I mean, sometimes there are details you'll have to figure out. But this is the skeleton of direct proofs pretty much all of the time. So the first thing that you do is you assume that the if part, or P, is true. And the second thing is, using this assumption, you want to show that Q is true, so that the then part must be true. And so, let's do a few easy examples. These ones aren't particularly difficult, but they do give you a good feel for how these types of proofs go. I think it's really good to be able to prove something that you kind of know is true already, and it's fairly easy, just so you can get the form of proofs down. And just maybe one more quick note. If you remember from a previous video, we said that a lot of times when there's an if-then statement, and this is kind of an if-then statement in disguise, I will rewrite this in a second, but there's a universal quantifier baked in there. So we're saying for all x that are, in this case, integers, if they're odd, then the sum is even. And so, since it's quantified, we're thinking of it as a statement, and we want to show that that statement is true, which means that the conditional part has to have this dreaded row never appearing. Okay, now that we're doing it, we have this example. Show that the sum of two odd integers is even. Let me reword this as a conditional. So, if, and let's add some variables here. If, let's say, m and n are odd integers, then m plus n is even. That's what we want to show. And from our previous video, we know how to write odd integers generally, and we know how to write even integers generally. So we have our if part here, and we have our then part. So we know what we need to show, and we know what we need to assume. So let's go ahead and do this. And usually you write the word proof down before you do one of these proofs. Okay, so we want to do the first thing, we want to assume that the if part is true. So let's assume that m and n are odd integers. Now, just assuming that is all fine and good, but we need a way to work with that. And a good way to work with things is expressing them algebraically. So we're going to use our ideas from the previous video to express these odd numbers, m and n, algebraically. Thus, let's say m equals 2 times some number k, some integer k, plus 1, and n is going to be, and this is important, 2 times a different integer, l, plus 1. Or maybe you wanted to use k1 and k2 or something like that. But anytime that variables could take different numbers, make sure to assign them as different variables. So that's very important. In fact, I'm going to make this note over here. K and L could be different numbers, so they are different variables. A very common mistake I see is students writing 2k plus 1 for both m and n. But say m was 5 and n was 7, well, m you'd write as 2 times 2 plus 1. 2 times 2 is 4 plus 1 is 5. And n you'd write as 7, which is 2 times 3 plus 1. So L here would be 3. So the number that you're multiplying by is different, and you want a different variable to say that it's not the same number. It's not necessarily the same number. Okay, after that aside, well, we've done the first part. We've assumed that the if part is true, and we wrote it in a way that we can work with. Let's do the second bit. Oh, I want to do this in black. The second bit, we want to show that the then part must be true. And I think it's a good idea when you're starting to learn proofs. Write what you need to show. So I like to do this as a little teaching tool. I just like to write to show. And what do we want to show? We want to show that m plus n is even. So what does an even number look like? Well, an even number is 2 times some integer. So we know whatever's in this bracket is going to be an integer. That's what we want to show. Now that we have that, we can actually do our work here. I'm going to erase this little note just to give myself a little more room. Remember, you're watching this as a video, so you can always rewind and go back if you want to see that again. Okay, so we know what we want to start with. We want to show that m plus n equals 2 times some integer. So let's start with m plus n. And we know where we want to end. We want to end as 2 times some integer. So we know where we're starting. We're starting at m plus n. We know where we're ending, 2 times some integer. And we just have to fill in the steps in the middle. And sometimes this requires a bit of creativity. And for a lot of people, this is very different from the mathematics that you've learned in high school. In high school mathematics, usually you know where you start, you know the steps to complete, and you're looking for the answer. Here's a little different. You know where you're starting, you know the answer, and you need the steps to show it. So it's a little bit different that way. But in some sense, if you think about it, all of this stuff that we've written down so far, this number 1 and what we've shown in number 2 so far, there's kind of no thinking in here yet. We've just kind of written the form of the proof. All of the quote-unquote work are filling in these steps. And usually, at least with the stuff we're doing in this course, it'll usually be a little bit of algebra to show this. As you progress further on in mathematics, sometimes it'll be more logical reasoning or dealing with some stuff that isn't algebra. But for our purposes, we'll be doing lots of algebra to get from the start to the end. Okay, so let's go ahead. We have m plus n, and we want to show it's 2 times some integer. We assumed that m and n were odd, so m equals 2k plus 1 and n equals 2l plus 1. And I want to use that assumption at some point, so I might as well use it right now. So I know m is 2k plus 1, so I'm going to replace m with 2k plus 1. Just to remind you guys, I'm going to highlight that here. There's my m. And then my n is 2l plus 1. And that's that. And you can see I put brackets around the 2k plus 1 and the 2l plus 1. Mathematically, those brackets aren't doing anything since I have a bunch of terms added together, so it doesn't really matter. But from a communication standpoint, it's kind of easier to see that the m equals the 2k plus 1 here and the n equals the 2l plus 1. So I just put the brackets in there so that when the reader reads this, they're kind of more satisfied that the m goes with the 2k plus 1, that I'm doing that substitution, and the n goes with the 2l plus 1. So it's a good communication tool to use some extra brackets if needed. Okay, so we know what we want the form for this to be, 2 times some number. Okay, so now we need to do a little bit of algebra to get there. So maybe let's combine as many like terms as we can, simplify this. Maybe I'll use black here, sorry. There we go. So we have 2k plus 1 plus 2l plus 1. I don't have any like terms besides these plus 1, so I'll add them together, and here everything else stays the same. So I have 2k plus 2l plus 1, which is plus 2. So I simplified this as much as I can, and this is good. Remember, I want to show that m plus n is 2 times some integer. So it'd be nice if I could factor out a 2 from every term I have. And in fact, right now, I can. 2k has a factor of 2, 2l has a factor of 2, 2 has a factor of 2. So I'll factor that out, and I'll just write this in blue here, just because 2k plus l plus 1 just factored out the 2 from the 2k, the 2l, and the 2. And what have I done? Well, I've written m plus n as 2 times some integer. I have k and l and 1. They're all integers. And if I add them together, remember the integers are closed under addition, so I get another integer. So I can say, since k plus l plus 1 is indeed an integer, and maybe I'll put some brackets around that just to say I'm considering them as just one number. Since that's an integer, then I know that m plus n is even. I've written m plus n as 2 times some integer. So I'll put a little box at the end here. That's kind of the hip way to say you're done a proof in mathematics. You put a little filled in or unfilled in box depending on style. So that box means the proof is done. You might see some other people just write the proof is done. Or you might see, instead of a black box, you might see QED. That's kind of a more old school way. It means something in Latin that I don't know, but you might see that at the end of proofs instead of a black box or a white box as well. Okay, let's keep going here. Let's do one more example, example 10.2. And we've seen a proof already. Maybe I'll get you guys to try this on your own at first, and we'll do it in stages. So first of all, try and rewrite this sentence, show that all integers have an odd square. Write this as a conditional sentence. So if something, then something else. So give that a go. Pause the video now and try that. Okay, now that we're back, and remember, you might have written it slightly differently, but I think the basic idea should be the same. So, reworded as a conditional, maybe something good to say would be if x is an odd integer, then x squared is an odd integer. So that's a reasonable way of writing this as a conditional statement. We know x, if we assume x is odd, then x squared is also odd. So that's what we want to prove. Okay, so hopefully you guys got something close to that. So let's do our proof. So let's do the first bit. Let's assume the if part is true, written algebraically. So maybe pause the video now and give that a go yourselves. Okay, so I would do something along these lines. Let's assume that x is odd. And what does that mean? Thus, x equals 2 times some number k plus 1. And I didn't do this in the last example, and I should have. But I introduced a variable k. I should tell you what that is. K is some integer, where k is some integer. K is some element of the integers. And that's good practice. I just forgot in the last example. You should tell people when you introduce a new variable what it is. Okay, so that's part 1. Part 2, let's just work out what we want to show. So again, pause the video, see if you can write down in a similar way to what I did what we need to show. Okay, now that you're back, we want to show that x squared is odd. What does that mean? Well, it means that we should be able to write x squared as 2 times some integer plus 1, where what's in the bracket is going to be, and I'll write it like this actually. I'm just going to write it as 2 times some integer plus 1. This is very informal notation. I wouldn't use this in a published paper or anything, but I think as we're learning, I think this is, if we're just having this line in here, this is fine for now. Okay, so you should have something along these lines. X squared is 2 times some integer plus 1. Okay, now maybe pause the video and see if you can write what we need to consider, where we're going to start and what we're going to end with. So maybe try that. So pause the video and give that a go. Okay, so we want to start by showing that x squared equals something, and that something eventually will be an odd number. So we should get 2 times some integer plus 1. So we know where we're starting. We're starting with x squared, and we're ending with 2 times some integer plus 1. So hopefully you have something like that. And again, if you think about it, all of this, there was no creativity, there was no real thinking involved, no real mathematics or logic or reasoning. This is just the standard setup for a direct proof. However, the next part is where you're going to have to be slightly clever. For these easy examples, it is more of a little bit of just doing some algebra. There's no real cleverness involved, but that's okay. So the last thing I want you to do, pause the video, see if you can fill in these steps here. How do we get from x squared to 2 times an integer plus 1? Remember, we know x equals 2k plus 1. We want to use our assumption. We made that assumption for a reason. So let's use that and then show that x squared equals 2 times something plus 1. So pause the video now and give that a go. Okay, now that we're back, we want to show that x squared equals some odd number. So let's replace x by 2k plus 1. Since we know x is odd, that's our assumption used. Now we want to square this. Okay. And as a reminder, well, what does 2k plus 1 squared mean? It means 2k plus 1 multiplied by itself. Let's do this as just a little side calculation over here. So we have 2k plus 1 times itself. And we multiply each term of the first bracket by each term in the second bracket, then add them all together. So we get 2k times 2k is 4k squared. 2k times 1 is 2k. That's the first term in the first bracket times the second bracket. And then the second term in the first bracket times the second bracket. 1 times 2k is 2k. And 1 times 1 is 1. And we can simplify that, combine our like terms, 2k and 2k. We have 4k squared plus 4k, that's the 2k plus 2k, plus 1. So 2k plus 1, all squared, is 4k squared plus 4k plus 1. Now we know what our answer should look like. It should be in the form of 2 times something plus 1. We have this plus 1 here, so it's probably a good idea not to touch this. So that's just staying. And we have to think, can we get the rest of it to look like 2 times something? And here, hey look, it'd be nice if there was a factor of 2 in each term, and in this case, there is. So we look at these, we can factor out a 2 from each term. Let's do it. We get 2 times 2k squared and 2 times 2k. And you can check if you multiply that 2 back to each of these terms here, you get 4k squared and 4k. All right, and we've done it. We just think we have a bunch of integers, 2 and k, and they're just added and multiplied together. So we're going to get another integer. That's fantastic. So we can write, since this 2k squared plus 2k is indeed an integer, then x squared is odd, and we're done. So hopefully you guys were able to do the steps as we went. And I will say, for a lot of people, proofs are a brand new thing, and it's one of those topics where you're just going to have to see a bunch and practice them to get the form down. But they kind of all work the same, at least for direct proofs. Again, you assume the if part is true, then show that the then part must be true. Because if you think about it, we're showing that when x is odd, when the if part is true, it must be the case that we can write x squared as an odd number. This is always true. There's no way that x squared could be written as something that isn't odd when x is odd. So we're never in that dreaded row. In this case, we're always in row 1, where the if part is true and the then part is true. So that makes the conditional true. We're never in that false area. So let's try another example on the next slide. So let's look at example 10.3 here. Remember that this Blackboard bold Q, that's the set of rational numbers, the set of positive and negative fractions along with 0. So as a reminder, I'll just write this over here. Remember that if we have a number r, it is indeed a rational number exactly when, if and only if, we can write r as some fraction where a and b are whatever integers that we like, and b, it can't be 0. So remember, rational numbers can be written as an integer over a non-zero integer. That's kind of the key for this. So maybe I'll get you guys to pause the video and try to do the proof all the way through. So we have an if-then statement already written, so it's pretty easy to set up. We know what we have to assume, and we know what we have to show. So remember that r and s are different rational numbers, so you're going to need different variables to describe them in terms of integer over another integer. So pause the video now and try to do that proof. Okay. Now that you guys are back, let's see how close we have our answers together. So the first thing we want to do, let's tell people we're doing a proof. And then let's assume the if part is true. So we're going to assume that r and s are indeed rational numbers. So what does that mean? That means that r is going to be a over b for some integers where b can't be 0. And s is a different rational number, so it's going to be described with different variables c over d, say. Again, you don't have to use a, b, c, and d. You can use whatever letters you like, as long as they're all different. Remember, if it's possible for the numbers to be different, use a different variable. And again, I introduced these variables a, b, c, and d, so let me tell you what they are. So a, b, c, and d are indeed integers, and well, we can't divide by 0. We can't have 0 in our denominators, so b and d can't be 0. Okay, so that is assuming that the if part is true. And again, since we're learning proofs, let's do a to-show statement. When you're writing things formally, you don't do this, but it's a good training wheel. So we want to show that the sum is a rational number. So we want to show that r plus s is some integer over some integer, and maybe I'll just mark down here integer that's not equal to 0. And again, just a reminder, this is pretty informal notation, but it's, I think, a good training wheel just so we know what we want to show. Okay, let's go ahead. So let's consider r plus s. Well, we know r equals a over b. We know s equals c over d. So let's replace r by a over b and replace s by c over d. That's using our assumption. Okay. Now we want to show that this is an integer over another non-zero integer. So we need to add these fractions to get it as one fraction. So let's get a common denominator. We'll multiply the first fraction, top and bottom, by d. And d is non-zero, so we can do that no problem. And same with the second fraction, we'll multiply by b, which is non-zero, so there's no problems there. So this is the same thing as a times d over b times d and b times c over b times d. So just to be clear here, I multiply top and bottom of the first fraction by d and top and bottom of the second fraction by b, just equivalent fractions. Oh, and there shouldn't be any equals there, of course. There should be a plus. Okay. And we know how to add fractions that have the same denominator. We just add the numerators. We have AD plus BC over BD. And now we just have to say that this is in the form of an integer over a non-zero integer. So let's do that. So since AD plus BC is an integer, and BD is an integer, and BD doesn't equal 0, and maybe it's a good idea to tell people why it doesn't equal 0, since I'll write it as B and D, since B and D don't equal 0. By assumption, that's what we assumed. Then we have that we've written r plus s as an integer over a non-zero integer. So then r plus s, that's the definition of being a rational number. So r plus s is indeed a rational number. Let me talk through this once more to make sure we get it. We assumed the if part was true. R plus s is a rational number. Here we are. R is a over b, s is c over d. We tell people what the a, b, c, and d stand for. These are integers, but b and d are also non-zero. That's very important. And you can see we use that later on. We want to show that r plus s is a rational number, so it's an integer over a non-zero integer. So we write out r plus s. We write r and s in terms of their fraction forms. We do a little bit of, let's say, fraction arithmetic to get it in this form, AD plus BC over BD. And then we have to tell people, well, why is that enough to show that this is a rational number? Well, we know AD plus BC is an integer. It's just a sum and product of other integers, so we're good to go. And we know BD is a non-zero integer. Well, it's an integer because B times D is an integer since B and D are integers. And we know it's non-zero since both B and D are non-zero. So we're good to go. Integer, maybe I'll highlight where I did this. So I'll do this in green. We're saying this is an integer here. And we're saying this is a non-zero integer here. Here's the integer part. And here is the Maybe I'll do this with a double underline. And here is the non-zero integer part. So we wrote this to convince people that we have indeed written r plus s as an integer over a non-zero integer. So it looks like our proof is complete. Let's do one final example here. So here we want to show that if n is odd, then 3n squared plus 8n plus 1 is even. Okay, let's do the same thing we did in the last one. Pause the video, give this a go yourselves. Remember that most of the things you're going to write without kind of thinking. It's just the form of the proof. It's just those few lines, at least for the easy examples, few lines kind of in the middle that you'll have to do a bit of algebra to figure out. All right, pause the video and give it a go. All right, so let's go ahead, tell people we're doing a proof. So let's assume the if part is true. So assume that n is an odd. And here I don't say it's an odd integer. Maybe I should have been a little more specific. But hopefully it's clear that I'm not talking about fractions. You really can't have odd fractions or real numbers. Odd is a property of integers. So let's say n is odd. So what does that mean? Thus, n is 2 times, I'm not going to use k this time just because I used k before. We can use whatever letter we like. So let's use 2 times, I don't know, g. Why not? Plus 1 for some integer g. Okay, we know it's odd. We're good to go. That's the first part. The second part, let's write down what we want to show. We want to show that this expression 3n squared plus 8n plus 1 equals 2 times some integer. Okay, so that's what we want to show. Let's start with 1 and show that it looks like the other. So let's consider 3n squared plus 8n plus 1. So that's going to equal 3 times n squared. I know n is 2g plus 1 squared plus 8 times 2g plus 1 plus 1. And again, maybe I'll write down here at the end, I want this to look like 2 times something, and I can fill in that later. As you do proofs more and more and you get more comfortable, you usually don't write this at the end. You just put it at the end when it's of the form that you need. But as we're learning, for our purposes, I'm just going to have this there to remind us that this is what we're working towards. Okay, so let's multiply this out. From the previous slide, we know what 2g plus 1 squared is. It's 4g squared plus 4g plus 1. You could do a little multiplication on the side to remind yourself if you like. So this is 3 times 4g squared plus 4g plus 1. And here we have 8 times 2g plus 1. So this is going to be 8 times 2g. I know what that is. That's 16g. I'll just multiply this out. Why not? Plus 8 plus 1. So let's multiply this through. We have 3 times 4g squared is 12g squared. 3 times 4g is 12g. 3 times 1 is 3. And we have our 16g plus 8 plus 1. In fact, I need a little more room, so let me erase this and just move it down one more line. And you can see why we really don't write what we want at the end usually, just because, well, we don't know how long our proof is going to be until it's done. I just wrote it there just to remind us when we're learning. Okay, let's combine our like terms. We don't have any g squareds besides 12g squareds, so that stays 12g squared. Let's combine our g's. We have 12g and 16g. That is indeed 28g. And we have our constants. We have 3 plus 8 is 11, plus 1 is 12. And we know that we want to get in the form 2 times something. Here we have 3 terms. Each of these terms has a factor of 2. We can factor out, which is excellent because that's what we want. Remember, as we're doing this, try and keep in mind what we're looking for. We're looking for 2 times a bunch of stuff, a bunch of integers. So we should keep in the back of our minds that we're looking for a simplification where each term, if possible, has a factor of 2. And looking at it like this, it looks like we're good to go. So let's go ahead and just factor out that 2. We have 6g squared from our first term left. 2 times 6g squared is 12g squared. From our second term is 14g. And from our last term is 6. And then we can write a little sentence at the end. This is indeed an integer here. So we can say since 6g squared plus 14g plus 6, since that is indeed an integer, we know that 3n squared plus 8n plus 1 is even. And we're done. And again, you can see that all of this stuff here, the part 1, the start of part 2, the first line where I say consider, and the last line, we know what that's going to be. All of the work is in what I'm going to highlight here. This is where the work is, right? So these steps here are the only place where we're really doing kind of algebra, mathematical thinking type stuff. Everything else is just writing down what you need to. So they're the only places where we're doing actual mathematics. The rest is just the form of writing these proofs. Okay, so hopefully you guys have a good feel for direct proofs now. The next video that we'll talk about is proofs by contraposition. And again, that is when we assume the then part is false and we show that the if part must be false, so we cannot be in that dreaded row.